All right, welcome everyone. It's exciting to have an in-person meetup. We had a few Java meetups the last 3 years, but this is the best attendance we've had in a long time. Yeah, my name's Sean. I am a software engineer at Netflix. I live here in Portland, work remote for Netflix. I'm part of the platform engineering team. I'm part of a subgroup that runs Cloud Gateway at Netflix. It's basically if you're familiar with an open source project called Zuul, it's basically the front end for all API requests that enter Netflix. So the gateway is responsible for things like authentication and load balancing and protecting the system from overload, things like that. Today we'll talk about micro benchmarking, and this is pretty important to the work I do at Netflix, because I work at the Cloud Gateway. We need the Cloud Gateway to be highly performant. So we use different techniques and tools for looking at performance of the system, and JMH is just one tool of many that you can use to evaluate a Java application. So JMH is a micro benchmark harness. It's an open source tool. You can find it on GitHub. Basically, Oracle has engineers that are still actively supporting JMH. And it's basically a way to run Java code and then measure the execution time of that code. And JMH will produce a report at the end of the execution to let you know how things turned out. And JMH is pretty widely used. If you look out on GitHub at any of these open source projects, you'll see that almost all of these projects have JMH benchmarks in the repo. So like, I'm sure many of you are using Log4j for logging. If you go look at the repo for Log4j2, there's actually significant benchmarks in there. The Log4j team is using JMH to ensure that Log4j is somehow optimal for logging use cases, because logging tends to be really important for most applications. Spring team uses JMH, and then at Netflix we have a few open source projects. I just highlighted 3 of them here, but Atlas is a time series database that we run at Netflix for more or less our observability platform internally. So the public repo for Atlas has a bunch of JMH benchmarks, and then Spectator is a metrics library for Java, very similar to Micrometer. In fact, I would say Spectator might be the precursor to Micrometer. But the Spectator library uses JMH to measure various operations. And then Netflix Zuul, which is part of our Cloud Gateway. So I'm actively working on the Zuul open source project. So it's near and dear to my heart. And when I started using JMH, my mindset was maybe counterintuitive. I thought, oh, this is like JUnit. Like, it's a way of just like looking at quality of the system or quality of a method. But if the documentation for JMH says that you should not think of it as JUnit. It's not intended. Like when I use JUnit, I typically will like write some JUnit code, write some assertions, and then I'll run the class from the IDE, right? And I often set breakpoints and then get, frequently you run it that way. JMH is a little different in that you're not really supposed to run if you have a suite of benchmarks, you don't run it inside the IDE. You basically have to package a special jar called a JMH jar, and then run that from the command line with some inputs. But JMH is pretty easy to set up. The thing to know about it is when you're setting up like a class path to use JMH, you typically are setting up a annotation processor, part of your class path, and that's because when the compiler is compiling your benchmark code, it's doing some code generation, which ultimately shows up in a jar file, your JMH jar file. This comment here is actually from the README file on the JMH open source project. They say that you should not run the benchmarks within your IDE. Generally speaking, when you're running benchmarks, you're trying to measure the performance of the code in a way that reflects the kind of hardware that you're running in production. So like to accurately measure your code, you might want to like actually take this jar file, maybe send it out to like an EC2 host or a Google Cloud instance, and run it there, because that is like production hardware. That's where your actual production code might run. So running it in the IDE is considered a less pure environment, and each developer is going to have a slightly different IDE configuration anyway. So, generally, if you need precise measurements, you might not want to run it from the IDE. But so I'll start with like a real world example. This is open source code on GitHub. This is the Netflix Zuul project. And about 2 or 3 years ago, one of the Netflix engineers, Carl, who's right there, he put together a JMH benchmark that is in a source file called headers benchmark.java. And the purpose of this benchmark is to look at one of the Zuul. Zuul has a class called headers, and we use this on every request and every response. So every time a request comes in the Netflix API, Zuul receives it, and then Zuul sets up a headers object to manage all the request headers. And then when it's time to send a response to the client, then we also set up a headers object for the response. So the performance of the headers class is pretty important. It's on the critical path for us. It is important that we read and write headers effectively. And so this particular file, if you're just getting started with JMH, probably the first thing you would do is start importing these annotations. In fact, every JMH benchmark that I've written pretty much imported this exact set of classes. And so that's at the top of your file. And then typically a benchmark also includes a setup. And much like if you're using JUnit, you've got a setup method. Well, this is a setup method for a JMH benchmark measurement that I'm trying to do. And the setup method, you may set up some test data that you're planning to use during the execution. And you wouldn't want all of this setup, takes time to execute. So you wouldn't want this setup code to be part of the benchmark that you're running. And so JMH allows you to separate setup code from actual measurement code. And that's kind of what this is. So this is setting up like an array of strings, and that array is the header names, because we're going to look at performance of the header class. So this sets up header names and header values, basically. And let's say the count was 100. So I'm going to have 100 headers. And then there's this this method that has the benchmark annotation. And that tells the JMH harness that this is what I want you to measure. You have to have that annotation there at benchmark. leave that off, then the harness won't take any measurements. But what I'm measuring is the average time that this method takes to execute, and the report is going to tell me the average time in nanoseconds. You could configure that. You could show microseconds, milliseconds, what have you. And the benchmark mode is also configurable. Some people prefer to use throughput as the benchmark mode. That's the one I tend to use. Throughput just tells me the number of times that this method was able to execute during some time period. So this is a really simple little benchmark. It's just instantiating the Zuul header object, and then it's adding like 100 headers into the object. And then at the end, it says return. And that return statement is actually very important. It might not be obvious here, but in JMH applications, a lot of the examples that are online will do exactly this. They'll return an object as the last line. And this is important because if I don't have that return statement, then the JVM might try to optimize the code at runtime. And sometimes the JVM will do dead code elimination. And the JVM will notice that the headers object is never used. It'll say, oh, there were all these calculations, but the header object was never returned to anyone. So there's no caller that's waiting for it. And if there's no caller waiting for it, then the Java VM might make an intelligent optimization and say, I don't even need to instantiate a headers object because nobody's waiting for that headers object. So by having the return statement, you're actually preventing the Java runtime from optimizing this method to nothing. And almost every tutorial for JMH will like warn you about this, because if you're new, like it's easy to like forget. And I've certainly forgotten. Yes.
So does this mean this runs in isolation? You're saying it's kind of like J, so there's nothing actually calling add headers to string, but because of these annotations and something within the framework, it's going to run this, measure it, give you an output.
Yeah.
But nothing is explicitly calling add headers underscore string.
Yeah. So this is all that I need to write. And then the JMH harness will do the rest for me. The JMH harness is responsible for invoking this method.
If you're in IntelliJ, you get a little playing symbol next to it that you can run, or is there another way you have to do this all?
So there is an open source project called the Micro Benchmark Runner, which actually plugs into like IntelliJ. I don't think that's been updated and recently. So I actually have just been running things from the command line, which pros and cons, but yeah, I'll show you some other examples that I've worked on more recently, but this is like the simplest example. This is something that we truly do care about in the Zuul project. We want to make sure that if you're adding headers, that we do it effectively. And we also, I'm only showing you a subset of this benchmark. There's other things in this. If you want to see more, like there's other benchmark things that we measure. We're interested in like setting and getting, or iterating through all the headers. Like there's different ways to utilize headers. So we have other measurements for those, but couldn't fit it on the slide. And then in the Zuul project, there's a build file, and this project actually uses a Gradle plugin. And I actually been using this plugin on a variety of projects, and I like it because it sort of pre-configures JMH for you. It makes it a little easier to set up a JMH project. But if you do use the plugin, then you have to have a declaration like this in your build Gradle file. And this tells the Gradle plugin how you want to use JMH. And that that line that says profilers, that is actually it's optional, but it's fairly significant for what our team was doing. Profilers equals GC means that I'm interested in object allocations. And when the benchmark is running, I want JMH to keep track of, how many objects have been allocated. Because in the cloud gateway, I want to handle as many requests and as many headers as possible, but I also want to minimize the number of object allocations. And so JMH will give you a report that tells you precisely like how many objects got allocated while your code was running. And this is useful as a developer because like I might want to rewrite the code. Let's say I rewrote the header class. I might want to then remeasure with JMH and then compare the existing implementation, look at how many objects it's allocating. And then maybe I have a new implementation like a pull request, and I can run a JMH measurements on that. And I can see which did I improve the object allocation rate or not. So it can be useful in that regard. So it's not just the speed of execution, it's also like how much you're working the JVM with objects. Anyway, so if you're ever like in the Zuul repo, you would typically run the JMH benchmark from the command line. So this is more or less how you'd go about doing that. And this is actually what this command is actually doing is it's actually invoking the Gradle plugin, and then that Gradle plugin then invokes the JMH harness, and then the JMH harness may spin off some JVM processes that go and do the work. And then those processes shut down, and the JMH harness is like recording the results of all the VMs that were created. It records everything and summarizes it into like a text file, and then puts that on somewhere on your file system. So if you're like looking to like learn JMH from scratch, probably the best resource I found was the README file on GitHub. I thought it was like a great starting point. It has links to like other things, but that's kind of where I started when I wanted to like figure out what JMH was all about. And from the README file, there's a link to a subdirectory called JMH samples. And this is almost like the best resource because it's like Oracle has a team of experts who wrote these examples, and each of these, there's like more than 20 of these examples in this folder, but it's sort of an incremental like learning style. Like they introduce one concept in each of the sample files, and then they have like a big block of a Java doc comment that explains like the nuances of JMH. And one of these like explains why you should have a return statement at the end of your method. Or if you don't use a return statement, there's like another alternative called a black hole. And then they have like a whole file explaining like what the black hole concept is. But anyway, I've actually spent some time reading these samples, and it's like a great resource, probably better than like, don't go to Stack Overflow. I think these samples are like much better. Like the depth of knowledge here is basically everything you need. I mean, I tried looking at Stack Overflow, but a lot of the answers were like 4 or 5 years old, so it wasn't like terribly useful. And recently, so I set up my own GitHub repo for like some things I just was playing around with. So my personal repo is called Microbenchmark Java, and I'm kind of like actively adding new things into this all the time. But I just wanted like a little playground space on GitHub just to upload some little things I was doing. And I think I have like maybe 14 or 15 benchmarks that I have in the repo, but these are the ones that I think are kind of interesting. Recently wrote a compression benchmark. And then I have an HTTP header benchmark where I'm actually testing Zool headers, but I'm also testing other header implementations from other open source projects. So like the Netty project has its own header class. The Spring framework team has their own header class. So I wrote a benchmark that compares Zool headers against Netty headers against Spring headers. And I won't tell you who won, but it wasn't that significant, but I didn't test all the use cases that I wanted to, so it's not really worth talking about the results right now. But anyway, so there's a lot of interesting little benchmarks that I wrote, but the one that we'll just breeze through here is the compression benchmark. So because I work on the cloud gateway team, you know, we take in all these HTTP requests and then we send responses, and we like to compress the response before sending it to the client. And if you look at browsers today, every browser in the world supports gzip compression. But there's a newer compression system on the web, which came out of Google. Shout out to Google, but it's called Brotli. And so like, as far as I know, like every major browser supports Brotli compression. I think Chrome was the first, and then Firefox and Safari followed on after that. And Internet Explorer doesn't exist anymore, so it sort of doesn't matter. But Brotli compression was designed by Google to sort of be the successor to gzip compression. So I wrote a benchmark that allowed me to measure the throughput of gzip compression in Java and compare it against the throughput of Brotli compression. So gzip is built into the JDK. There's already a class in the JDK called the gzip output stream. And I think it's fairly well optimized because it's been in the JDK for forever, as far as I know. The Brotli, there's a Brotli library called Brotli4j, which is basically written by a guy at Apple. And the code is on GitHub. And anyway, the Brotli code is interesting because you can call it from Java. And Brotli is a compression algorithm that supports different parameters. So you could tell Brotli that you want maximum compression, which will take a little longer to do. Or you can tell Brotli, just do it quick. And if you only save a few percent, like that's good enough. All we care about is speed. And so the range of this, it's called the quality parameter in Brotli, and the range is from 0 to 11. So 11 is maximum compression, and 0 is like the weakest compression. So I wanted to write a benchmark that compared gzip against Brotli at quality 0 versus Brotli quality 4 versus Brotli quality 11. So when you're using JMH, it's very common to like set up a Java enum. So I declared an enum class because I wanted to use the enum as a parameter in the benchmark. So on the next slide here, you can see I'm using an annotation in the middle of the screen there. It says @param, and then private compression type. So I've declared compression type as an enum class, a Java enum. And so the JMH automatically knows how to handle an enum. So it's going to run my test with all the permutations of that enum, because I've put the @param there. If I forgot to put the @param there, then it's not going to run any permutations at all. I've also parameterized the size of the string. So here I've got it's 100,000 characters in a string. But I could also parameterize this. I could say, oh, show me a string of length 10, a string of length 100,000, or a string of like 10 megabytes. And maybe I want to run the benchmark against all those permutations. So basically, this is the benchmark. I set benchmark mode to throughput because I want to know how many times can I run this compression per unit of time. This is more or less what it does. So JMH is invoking this method because it has the benchmark annotation. And all this does is it sets up an output stream. And then I look at what the compression type was. Maybe it's gzip. And I'm asking it to give me, this is an interface called compression operations. I had to write that, but it's an interface. And then I implemented it with some gzip code. And then I call the compress on the operation class that basically will take that array of bytes, 100,000 bytes, run the compression, and then JMH will measure how long that took. And you can see here, these last two lines, you notice I don't have a return statement at the end. I'm using what's called a black hole object. So there's a parameter up there called the black hole BH. That's a feature of JMH. And that's like, if you want to, well, the problem with the return statement is you can typically only return one object. But like, what if you had more than one object and you want to mark it as like important or something, and you want to ensure that the JVM doesn't optimize it to nothing. Anyway, so there's a method here called consume, and I'm basically telling JMH, please consume this object because I don't want dead code elimination to happen. So that's more or less what that is. I wish I had a better explanation, but I'm not a black hole expert, so it's sort of a mystery what the black hole does. They don't. I mean, you could go look at the code, but they describe it as magical. So that's how I look at it. So when you run the benchmark, it will like print out like this header information as this is part of the report that comes out of it. But the report will always tell you what version of JMH you were running, what version of the JDK you were running. It will also tell you how many warm-up iterations you configured. And this is completely up to you. If a warm-up iteration is like, tells JMH, oh, go run that method, twice. But the final report is not going to include the warm-ups. It's like if I was in the Olympics, I was running the 100-meter dash at the finals, I might go warm up on the track, but no one's gonna like publish those results. That's what the warm-ups are in JMH. They're not really part of the final result. But then after the warm-up phase, then it goes to the measurement phase, and that's where it's running multiple iterations of your method and keeping track of the time, and then showing you that in the report. And this benchmark, I've also configured it just to be single threaded. I don't really have any shared state that like these compression objects are not, there's not like 10 threads accessing a single compression object. So it didn't matter to me. I didn't need more than one thread. There's other benchmarks that you might write where you do care, because you might have some data structure that you want to be like, I don't know, if you had like a concurrent list of some kind, concurrent hash map, and maybe you want to measure the performance of a concurrent hash map with 10 threads. JMH lets you do that.
Yeah, Sean, let's say you added parallel to your compression function, and you're compressing a string parallel, and the benchmark actually it got slower. Would JMH let you like debug that and see where the dependency is that's causing it
JMH doesn't
Or I guess what
help
tools
you
would you
see
use?
that like that. I mean, you might do some other profiling. Um, there are other like profilers that you might use to do some other instrumentation.
Oh, yeah, like IntelliJ has that, right?
Yeah,
Okay.
it does. And then the last line here is just benchmark mode. I'm measuring throughput operations per unit of time. And these are the results. This is actually what you get as the default output from JMH. And you can see here that it printed out this great table, shows me all the different types that were in my enum. And then I hard coded the size to just one value. And then it gives me the score. So that score is a number, and that number is operations per millisecond. So gzip was 0.089, and Brotli 0, which is the fastest mode for Brotli, was 1.5. But Brotli 4 is sort of in the middle, and that's actually the default. Brotli Quality 4 is the default for the NetTie framework. So by default, NetTie will always do Brotli compression at level 4. But anyway, that's still, you can see level 4 Brotli outperforms gzip. And then if you really want to go to 11, you can, but you pay a penalty to get. So the compressed data might be maybe a better compression, but you're spending more time doing the work. Now I've run this benchmark on my laptop, and I've also run this benchmark in the cloud. But I haven't run this benchmark on the actual production hardware that I use at work. So these numbers are like a starting point, but for me to like really like value what the numbers are, I might need to run this on like an actual EC2 host that, or Google Cloud instance, where my production workload runs. And running it on my laptop, I mean, I guess it's valid numbers, but it's not the same as what my laptop's not running in production, not that I know of. So the numbers off the laptop should never be your final numbers. Maybe there's just a starting point if you're just getting started, but if you're really like serious about performance, go take the JMH jar, go copy it up to an actual server class machine, and then run it there, and then get the report off that machine. Because there's a lot of variables here. If I'm just running on my laptop, who knows what version of the JDK I have? It might not reflect what we deploy to prod. But also, the number of CPUs and other things. And if my laptop's not plugged into the wall, I don't know if I'm getting the full CPU speed anyway. So like, don't run JMH benchmarks when you're on battery, because it might not reflect reality. But there's some other things about this benchmark that I haven't really finished. So like this payload of 100,000, that's just sort of a number I pulled out of thin air, but that might not reflect what's happening in my prod environment. What if my prod environment is largely like 1 megabyte JSON responses? Well, I haven't benchmarked what a 1 megabyte JSON response, looks like when it's compressed. So this test is sort of synthetic. It's artificial. It doesn't reflect the kinds of JSON payloads that happen in prod. In fact, when I wrote this test, it's not JSON at all. It's just a string of 2 letters, A's and B's, because it was easy to generate A's and B's. But that's and who knows, maybe like there's a better test would be to actually have like a JSON doc that's 100,000 bytes, and then maybe a JSON doc that's a megabyte, and then run this benchmark against those files because that would better reflect reality. So that's one way to think about it. Another thing about running this benchmark is that I only ran a few iterations when I was taking these measurements, but you could set up the JMH to run like 1,000 iterations, and it would take longer to run it, but you'd get more data points. And the more data points you have, I think, the more you can trust the results. So, because I'm a lazy developer, I just wanted this benchmark to run fast. So I put a small number of iterations. But, for certain kinds of tests, it might be worth bumping up the iteration count. Depends on your.
Sean, if you look for like an observer effect, like does the benchmark, in terms of what it's actually doing behind the scenes, it's just like a thread that's waiting for this process to finish, right? Like it's not actually, does it actually slow down your code too by running the benchmark?
So I'm not really an expert on JMH internals, but JMH tries to run all these sequentially. It's not trying to run gzip and Brotli in separate threads. It basically has like a runner thread, and it will run all the iterations for gzip, collect all the measurements for gzip, record those, and then it'll go on and do Brotli 0. And so actually when the test is running, you can watch it just print out that it is sequentially just doing these in the order that's actually printed here. But they don't really have, it's not like there's multiple threads all trying to do all of these things in the fastest way possible. Because you'd have thread contention, or, if you had some Brotli thread running and some gzip thread running, like if they're running.
But yeah, I've seen so much
get-
benchmarks, you have like this nice bird effect where the benchmark itself actually takes away resources from that.
Yeah. Yeah. And the JMH documentation also says, like, if you're really serious about benchmarking, like, don't have other things running on your machine. Cause you're not accurately, who knows what you're measuring at that point. In fact, I've run this benchmark as part of a GitHub Actions workflow, and the code runs in GitHub Actions on a GitHub Action runner host, but I have no idea if that's repeatable, because each time you invoke GitHub Actions, who knows what it's provisioned, and who knows if there's noisy neighbors, or you could get different hardware each time you're running in GitHub Actions. So the results that I've seen in GitHub Actions, I don't fully trust them because they're probably not reproducible. But if I ran 1,000 of them in GitHub Actions, maybe, yeah. The thing about GitHub Actions is they don't tell you what hardware you're running on underneath. So don't run everything in GitHub Actions and look at the results, because you don't know what they've allocated to you, and you don't know if you're being throttled on that host. That being said, so I do actually have run it in GitHub Actions, and this is an execution that ran this afternoon. But each time I run it, the results are slightly different, and I have no idea what CPU is running my code underneath. I mean, it's Intel hardware, but GitHub is deciding.
You can set up an external.
Yeah.
You can take your own hardware and then follow the remote runner app and be in charge of executing.
Yeah, provisioning your own runner might be better than what I've done here, because then you control the hardware and you know exactly what it is. But yeah, so there's a whole bunch of things I was doing as an experiment here, but it's not reflective of like the production environment that I actually care about. So that's probably all I really had. Yeah, so that was more or less the end. I'll just wrap it up there, but yeah, if you're interested, go to Micro Benchmarks Java.
I was wondering if you have any like examples off the top of your head of like big or surprising results that you've gotten from that micro benchmark. This stuff.
I've actually seen my laptop perform really well. Um, uh, in fact, so I was looking at something today where I'd run a JMH benchmark on this MacBook Pro with the M1 chip, and I ran the exact same benchmark in GitHub Actions. And when I looked at the report, it showed that on this machine, it detected 10 CPUs, and then it set up 10 threads. Because one of my tests in JMH, you can say, run this benchmark with the maximum number of threads, and then it like calculates what it thinks the max threads are for your hardware. So it said that I had 10 CPUs, and JMH set up 10 threads and ran the benchmark. And I ran the exact benchmark at GitHub Actions, and it said that GitHub Actions provided 2 CPUs, and it could only set up 2 threads. So the results of these benchmarks aren't equivalent. So looking at one report versus the other is like apples and oranges. But yeah, at the end of the day, it's always better to like provision some like dedicated hardware and they go like run it there. Because like in our environment at work, there's a certain instance type that we use in the cloud. Has a certain memory profile and whatnot. And so that's really where I want to like take measurements.
Have you like used any measurements though to like make important changes to the gateway application?
So the first example I showed of the headers benchmark, that was written like 3 years ago by a coworker. I mean, that was used as sort of an exercise to like improve the way that we set up header objects. And I believe that I wasn't at Netflix at the time, but legend has it that like we figured out how to allocate fewer objects. And for at our scale, like that matters. If you had billions of requests coming in and you can save some allocations, then I guess you're saving money somehow. You're burning down fewer, I don't know, trees. I guess I'm not sure, but yeah, that's one example. But also, like, there's some other benchmarks out on GitHub. Like, there's a cache library called Caffeine, and they have a really good benchmark suite where the author of Caffeine, who used to work at Google, he wanted to prove that the Caffeine cache was better than any other cache. So he wrote a benchmark where he evaluates like, I don't know, 5 different cache libraries, and Google Guava was one of the 5. I forget what the others were, but anyway, if you trust the benchmarks that are in that repo, like it measurably shows like that Caffeine performs really well, better than Guava. And so like you can use this to like make decisions. Like if you were looking for a really good caching library, you could do an evaluation, like your own benchmark that reflects however you're planning to use the cache, and then choose an open source cache library based on the results. So it's not only about optimizing the code, it could be about just choosing the best solution based on some measurements that you take.
Just on the same comment, if you want to test your application in multiple instance types, which are the cloud, would there be a use case for this?
Yeah, I mean, that would be useful. I mean, if you wanted to look at, you know, the cheapest instance type versus the most expensive instance type, and maybe you want to measure something. Well, you could just have some code that, but again, maybe that's just a synthetic benchmark, and maybe you're better off running your full-blown app. But it depends how easy it is to like provision your full app. Where I work, we do a lot of Canary deployments, and we also have a Canary analysis platform called Kayenta. It's sort of like part of the Spinnaker project. If anyone's using Spinnaker, there's a sub project off Spinnaker called Kayenta. Kayenta does Canary analysis. So like I can set up a Canary and prod that is of a different instance type than our standard instance type. And then I can run that Canary for like an hour. And then I can generate a Canary report from Kayenta, and it will show me the differences. That's a more realistic way to like truly evaluate new instance type. And most cloud providers are always adding new instance types. And sometimes you want to go find out if the newest instance type is worth the money. Are you getting a 10% gain, or are you getting a 40% gain? And it's best to like go run your app, find out.
So, quick question on every time we run a benchmark, lots of underlying factors, maybe environment, runtime environment, kind of contribute to the purchasing price. So is there like, do we have a provision to change, for example, change the RAM, change the memory, or change the number of CPUs, or so on? Can you also make them parameterized?
JMH, the JMH harness doesn't give you any of that. No, like JMH is all about just producing a jar file, and then you could decide to go copy that jar file to server A and server B, and then execute that jar file in both places and get a text report out of it. But it's not like a feature of JMH. But you could also use it to maybe evaluate different versions of the JDK on the same hardware. Like in prod today, I'm running JDK 17, but maybe next month I want to use JDK 19. Well, maybe there needs to be some way for me to like, I want to evaluate both of those. And if I had a JMH jar that I trusted, and I could run it on both JVMs and see if they're similar. Like my header benchmark, run that on JDK 19 and see if the numbers are equivalent. It might be, but I haven't really looked at it. Cool. Thank you.
All right, so I'll take just about 20 minutes and zip through this presentation. Okay, so my talk will cover two areas, which is, first is, if you are running your Java app, where would you run it in the different clouds, right? So I'm trying to be not Google biased here, so I'll cover all the clouds. And if you know Azure or AWS, tell me if those are right or wrong, right? And secondly, nowadays, container images have become the standard to package your Java apps, right? So we will go through some approaches to package the app. Again, if you are doing something different, let me know and we can discuss that also, right? Okay, so let me skip through a bunch of stuff. Take any cloud, you can bucket the way you run your app into these three categories. Right? You can run your app in a VM, you can run it in a container, or you can run serverless as functions. Right? There is a difference between what is termed as fully managed and serverless, and you can quickly read through it. I think I will not go through it, but just understand that there is a difference between fully managed and serverless. Serverless, you typically don't even see the machines where the stuff is running, right? You submit a function in AWS, it just runs. You submit a function in the GCP environment, it just runs. You don't know what kind of machine it's underlying machine it's running, right? So that is serverless. It's typically pay model is by request. because again, you don't have a resource to pay for. So it is typically by request. Whereas for fully managed, there is you have visibility into the machines where the code is being run, and you pay by resources, right? So though that is a sort of very high level difference between fully managed and serverless. Given this, what are the VM container types, server types on GCP? VM is compute engine. You may have run your Java app straight on a computer engine. I'm not sure what Apex does, Todd.
I'm on the on-prem stuff.
I see. Oh, okay.
This is
All right.
new to me.
So I'm sorry. GKE. All right. So containers, yes. GKE is the premier option for Google Cloud. But one more option, one more way of running a container is using something called Cloud Run, which is a serverless version of running a container. Right? So that's why I touched on what's fully managed and serverless is. So GKE is the fully managed version. Cloud Run is a serverless version of running a container. Pure serverless, we have Cloud Functions and App Engine. App Engine is not getting too much developer love nowadays. So if we are working with customers, we typically tend to recommend Cloud Run as the runtime. Right? So this is on the GCP side. AWS side, I think Sean, you have to correct me here. So AWS VMs, it's EC2. Containers, EKS or ECS, both of them run the containers. There is a serverless version of both EKS and ECS, which is a EKS with Fargate and ECS with Fargate. Right? And finally, if you want to run your functions, Lambda is the solution on AWS. Not sure if I'm missing anything. People who use AWS here. Sean, do you? All right, so let's assume that this is right. Okay, Azure. I have absolutely no clue about Azure, and I Googled this information and got this information out. So VMs, virtual machine. Containers, you have the Azure Kubernetes service. That's your Azure container runtime. They also have a serverless version of a container runtime, which is referred to as Azure Container Apps. And finally, Functions. Azure Functions is the pure serverless version of how you would run a Java app on Azure. Right? Again, trying to be not completely biased to Google. Okay, which runtime would you select? It's a consultant's answer. I think all of you know what a consultant's answer is. You should pick it up here. It depends. That is the consultant's answer, right? So there is no right answer. It depends on a lot of factors, level of abstraction. If you want control over the OS, then you may choose VM. If you are okay with less control, you may choose serverless. Use cases, if it is a legacy app, you may go with a VM. If it is event-driven, if you need to do just one thing, you may go with a serverless kind of a solution. Right? Team dynamics, your team may be completely ops-oriented. There may be somebody who can run that clusters, run the bare VMs. Then VM may be the right solution for you. If it is a dev-oriented team who doesn't want to sort of focus on administration management at all, then serverless may be the right fit for you. Billing model, if you're comfortable with paying by resource, again, paying by usage, serverless may be the right fit for you. If you are comfortable with paying by resource, VMs or containers may be the right fit for you, right? So these are, again, it's any of these factors may be applicable to you, and you may go for VMs or containers or serverless. But again, containers are the most popular option nowadays. So if you want to package your Java app, these are the 4 solutions that I have personally worked on. You may be aware of more. If you are, just bring it up as we go along, right? I'm not going to touch Docker files here. I'll cover cloud native build packs, Jib, and GraalVM is a different kind of an animal altogether, but it may, if you have not worked with it, it may interest you quite a bit. Okay, so cloud native build packs. Cloud native build packs is a very interesting project. What it does is, given a source code, given a Java-based source code, it can create a OCI image without requiring any Docker files whatsoever. Right? The way it does it is using a bunch of concepts. The first concept is of something called a build pack. Build pack essentially has 2, let's call it processes. The first process is detect, does the build pack support this source code? Right? That is what it does. If it supports it, then the build step is called. right? For example, one example of a build pack that I can think of is if it is a Java-based code base with, say, a pom.xml in there, that means it's a Maven based source code, right? So if there is a build pack for Maven, that will act on it and compile the code and everything else, right? That is exactly what a build pack is. Now, a series, there is a concept of a builder. Builder is nothing but a set of build packs, right? And a lot of different companies provide builders. Google provides one builder, which can create the container image little suited to the Google Cloud environment. There are builders for that Heroku provides. There's a builder that Pivotal used to provide. If you've worked with Pivotal before, now it is called Paquito, by the way. So these are all so builders is nothing but a set of build packs. Just think of it that way. Stack, let's not touch on it for now. And finally, the platform puts all this together. It takes the source code, it takes a builder with all the build packs in it, it takes the stack with the base image in it, and creates your app image, right? So that is the entire flow of a build pack. I'll show you an example that'll make things a little better. But again, the basic concept is, given your source, without too much effort, you can generate the container image out of it, right? Okay, let's skip that. Jib. Jib, I personally like it a lot. When I was working at Nike, this is the tool that I used for creating the images that were deployed for Nike's application. And Mark and I worked together at Nike, so Mark will be familiar with that. So it is very interesting. Similar to build packs, it doesn't require a Docker file, and it can create the image for you. It is pure Java. It doesn't have any native dependencies whatsoever. It just comes as a Gradle and Maven plugins. You just add those plugins and it can create the image for you. It doesn't even require a Docker agent, right? It understands the Docker's zip format natively. So without even a Docker agent, it can create the image for you, right? And one advantage of not requiring a Docker agent is sometimes you run into a situation where, say, GitHub Actions, right? GitHub Actions is running in a Docker as a Docker container. You require another Docker from within a Docker. So it's called Docker within a Docker to be able to create that image, right? Jib doesn't have that problem because it doesn't require a Docker agent at all. Okay, so that's Jib. GraalVM is very interesting. It's really hot right now, but again, I'm not entirely sure if it is ready for production though. What it does is, given a source, it creates, from a Java source code, it creates native binaries for Linux, Windows, Mac, everything else, right? So again, from a perspective of running in production, you may typically create a Linux binary, package a container around it, and then use that image to deploy to containers, right? So I'll show you the advantage of GraalVM. You can imagine the advantages. Because it creates a native binary, it is going to have much faster startup, not like JVM, which can take a long time for the JVM to boot up, then your application to boot up within that, right? So it can typically take 3 or 4 seconds before your application boots up. With GraalVM, it is sort of instantaneous. And because it's a binary, because there is no JVM packaged with it, it has a sort of a very small footprint also. All right, so that is the entire presentation. But now let's go into the demos. All right. So what you are seeing is a Spring Boot based Java application. It has one endpoint which just responds with a hello. And just to make sure that you believe me that it is an actual code that I'm modifying, let's put it as hello Pjug, March 2023. Right, and the way you start this is a Maven based project, so I would use Maven to start up this project. And let's start it up. And one thing that I want you to observe here is the amount of time that it's taking to start up the application, right? So it's taken about 1.7 seconds to boot it up. I can hit the endpoint. Let's do I'm going to hit one of the endpoints, and it's going to tell whatever I just typed in, hello Pjug, March 2023, right? So now, how do I convert this Java application? How do I create a image for this Java application, right? So let's start with build packs. And build packs has comes with a command line tool called pack. If you search for cloud native build packs, you will see this tool show up. It's in the getting started, it should show you how to install that pack tool. But assuming that you have installed the pack tool, the way to create an image is this way. Let me copy some code. 1 second. All right. So this is how you would build an image. Right? Again, you can see that I'm not specifying a Docker file, nothing. I'm asking it to build an image called sample app Paquito with the path of the source code being this one, providing it a path to the builder. Again, a bunch of companies provide the builders. Google does, Heroku does, Paquito, a company called Paquito does. Here I'm using the Paquito ones. And also I'm specifying that it should use Java version 17. Otherwise, for whatever reason, it defaults it to 11 even now, right? So here I'm specifying that it should use Java 17. If I run it, what you would see, oh, okay, it's going to take time, but let's let it go a little ahead so that I can show you at least the concept of a build pack. Right before the demo, I had done a Docker system prune and it's removed all my cached images. That's why it's pulling it again. But yeah, so if you look at it, here it is where it detected a bunch of build packs. It detected a bunch of build packs. It called the detect step and only the relevant, so these are the relevant build packs on which it's going to call the build step. Right, so there were 10 build packs that were relevant for this code base, and it's going to call the build step for each one of them. Right? And at the end of it, it's created the image. And if I look at my images, you would see, let me maximize this. Okay, you would see the sample app Paquito image created. It has a size of 298 MB. That because it has to package the base OS, it has to package the JVM, and on top of that, it has to put the app. That's why it's so large, right? 298 MB. Now, just to show that it's actually our app, let's run it. I'm going to run it on port 8080 and then call sample app Paquito latest.
Or would you have to say like 43 years ago? On the-
It's for repeatability that it doesn't put the timestamp in that,
Oh, so-
right? So otherwise, if it puts a timestamp, every time it creates the image, the time is going to change, right? So it cannot really cache it at that point. So deliberately, it puts a very old time in it, right? So that metadata doesn't change. So that image is the exact same image. If you run it, say 2 days down the line, it's going to be the exact same image, right? So that's why that it puts a crazy timestamp in it. All right. So if you look at it, it took about 3 seconds to run through. Again, if I hit my endpoint, you would see that it is indeed the code that we just created, which was containerized, right? Okay. So let's go back. All right. So this is Paquito. Jib is much simpler than this. All you require is a Gradle plugin, which looks like this. Right. So here I'm telling that I've pulled in Jib Maven plugin and asking it to create a Jib demo project. And once I have that, all I need to do is call Jib. Okay. So this is what I do. I call a Docker build task of Jib. If I want, I can provide it the coordinates to my repository, right? Docker Hub or Artifact Registry, and it'll actually publish it directly there. But here, I want it to publish it to my local Docker. That's why I'm giving the explicit Docker build command. Otherwise, I can just call Jib build and it will push the container image to the appropriate repositories, right? But just to show what it looks like, hey, that's it, right? It took barely any time and it created the image for me. Again, if I look at the image size, it will be around the same size as the one created using build packs, around 287 MB. So it's still large. And again, it would run the same way as the build pack one, right? But again, it is very convenient to run on a build server. That's why I personally prefer to use Jib as my container image tool. Finally, GraalVM, right? GraalVM is a while to run through, but once it runs through, I've created an image using GraalVM. If you look at it, it's actually much smaller than the other two. It's taken about 94 MB versus 298 MB with just the Java part of it, right? And the neat part is if I were to start it up, right? So let's start it up. Docker run. Oh, nice. It took a good time for it to freeze up. Just give me 1 second. It should still, okay.
It's just the environment in which you like work in usually. Like this.
So I'm using something called Cloud Workstation. So it's a cloud-based IDE.
Yeah,
If you've used GitHub Spaces, Code Spaces, I believe,
I tried it.
it's similar to that. It's similar product from the Google side. So I'm not really running it on my my machine. I'm using the Cloud IDE to run entirely.
That's what you do on a regular basis. Though, right?
I don't actually. I use my own machine, but yeah, it's a cool tool to demo out for sure. Because if I were to present as well as compile on the same machine, the presentation is going to freeze for sure, right? So, okay, let's run it once more. Docker run -p 8080 Jib. So this time, what you would see is this. Just look out for the startup time, and what you would notice is that it should start up much quicker than the other ones. See, 0.117 seconds versus 3 or 4 seconds that it took before. It's actually even, let's try just once more just to see the speed of it. 0.056 seconds, right? So it is ridiculously fast, but it has a lot of catches, though just not all Java code can be compiled into GraalVM. Just remember, say for example, if you use a lot of reflection in your code base, it won't compile that well to GraalVM. GraalVM has to be told which classes are available at during compile time. And because of reflection, you bypass all that, right? So that's why not all code bases can be converted to GraalVM code base, or you have to provide it a lot of hints for it to create that image for you. So just keep that in mind. All right, so now deploying the image. So I'll show one thing to deploy this code base into one of the runtimes. Let's take Kubernetes, and I'll deploy the same code base into Kubernetes just to show that it's sort of very easy to do that. And here, what I'll do is, have any of you worked with a tool called Scaffold by any chance? Oh, okay, nice. I see. So what Scaffold does is, it wraps a bunch of things together. It wraps, so when I want to deploy to Kubernetes, I need to create the container image, put the name of that, the coordinates of that image into the manifest the deployment manifest for Kubernetes, right? So I need to plug in the image name into this deployment. This image has to have the coordinates where I have published my image, right? And then where am I deploying this to, right? I may be deploying it to a GK, I may be deploying it to a Cloud Run. What Scaffold does is it wraps all of that together, right? So in a single go, I specify what my images are, where should it publish it, how should it create the image? So here I'm saying it should use Jib to create the image, and then finally deploy it to Cloud Kubernetes, right? So it wraps everything together. And if I execute it, I'll execute it in two parts. The first part is where I publish the artifact into a repository. In this specific instance, I'm going to publish it to Google's artifact registry, which is the repository that Google provides. So let's quickly do that. Should not take too much time.